So a couple of weeks ago, Sebastian was giving a talk about conserved quantity theories of causation and arguing that if the conserved quantity theorists helps themselves to notions of approximate conserved quantities and approximate symmetries, then they're able to dodge several of the objections which have been raised against them in the context of general relativity. Sebastian also very briefly alluded to pseudotensors. And the thought with pseudotensors is that these objects are pathological for various reasons, which I'll talk about in this talk, which makes the notion of local energy conservation in general relativity problematic itself, since the objects which are supposed to represent gravitational stress energy in general relativity are pseudotensors. So a second line of potential defense of the conserved quantity theorists was, if you can argue that pseudotensors are less pathological than they seem, then that would again provide the way of giving more, getting the conserved quantity theory off the ground again in the context of general relativity. All of this is really just to say that pseudotensors actually form quite a substantial part of the discussion of my work with Sebastian. They also form quite a substantial part of the work that I've been doing with Caspar Jacobs, which is what I'm going to be talking about today. But the angle here is a little bit different. The angle is something like, even if you think that pseudotensors are pathological, and so on the face of it, the notion of gravitational stress energy in general relativity is problematic, actually you might be able to use pseudotensors to construct something which doesn't have the same pathologies and which might be a candidate for representing gravitational energy in general relativity. So that's the kind of stuff that I want to talk about today. But the way that I'm going to frame this is by engaging with a debate which I think most philosophers of physics, at least, will be unfamiliar with, which is a debate about absolute representations. It's a debate from pure metaphysics. So the kind of people who have been engaged with this are, for example, Bernard Williams, one of the most famous philosophers of the 20th century, but obviously not a philosopher of physics, and also Adrian Moore, my colleague at Oxford, also an exceptional philosopher. Both of these authors, but in particular Moore in the first third or so of his lovely book, Points of View, argue that absolute representations of the world from no particular point of view are possible. Moreover, these people argue that it's the business of physicists to try and construct such things. If I could only represent physical goings on from my point of view or from Jamie's point of view, then there would seem to be something missing. Physics should strive for greater detachment than that. So here's what Moore writes on this topic. It's the business of physicists, as it's the business of no other inquirers, to find some minimal set of concepts that can be used for the indirect endorsement of any true representation. Evidence that the concepts physicists currently employ are inadequate for these purposes is evidence that they have further work to do. There's some Moorean jargon here, indirect endorsement, but the idea, I think, is relatively clear. So the way that the talk is going to pan out is this. I'm first of all going to say a bit more about this Moore-Williams line, arguing for the possibility of absolute representations. I'm then going to present to you geometric and non-geometric objects, and in particular pseudotensors, these things which are supposed to represent local gravitational energy in general relativity, are non-geometric objects. And we're going to see how anything which is represented by a non-geometric object doesn't seem to admit of an absolute representation in the Moore-Williams sense. And so there seems to be a tension. On the one hand, Moore and Williams are saying absolute representations are always possible, but on the other hand, certain objects in physics don't seem to allow for absolute representations. So the talk is really about trying to square that circle. Now, there are different ways that you think that the Moore-Williams argument is right. One thing that you could do, and this is a very popular line, is to say that actually the things supposedly represented by pseudotensors and other non-geometric objects are actually just junk. And that's often the way that people go in the context of general relativity, where they say, well, local gravitational energy just doesn't make any sense in that theory. Another way that you could go would be to try at least to construct something which does qualify as an absolute representation of gravitational stress energy, or whatever it is that you're interested in. And that's what I'm going to try and do in the second half of the talk, where I'm going to define some things on the bundle of linear frames and at least argue that that seems to qualify as an absolute representation of gravitational energy in general relativity in the Moore-Williams sense. Cool. So hopefully that's relatively clear. So let's crack on. I have to say that these slides are from an hour-long version of this talk, and so I am going to skip some stuff in the first section because I think it would be better to talk about the physics than about more exegesis, but we can come back to things which people are interested in. Okay, so absolute representation. So Moore's book is lovely, but it is quite dense, but it has the merit of having a glossary in which he defines all of his technical terms. So here are some of the relevant technical terms which he uses. So first, a representation is anything which has content and which, because of its content, is either true or false. So it could be just, I am in Oxford, something like that. To integrate two representations is to produce a third representation whose content is the product of theirs. In other words, a representation which is true if and only if they're both true. So I can say something like, I'm in Oxford and I'm in the UK. Both of those are true representations, and I've integrated them just by conjoining them. That idea of conjoining two representations is what Moore calls integration by simple addition. So that's basically just literally conjoining them in the way that I just described. Now, it's going to be the case that some representations are integrable, but not by simple addition. So if you're moving with respect to me, say, you might say James is moving, I might say James is at rest. Of course, we can reconcile those things pretty easily, but you can't just straightforwardly conjoin them and say something true. So you have to try a little bit harder to integrate some representations than to integrate some other ones. For Moore, a point of view, this is literally in his glossary, so you might find it's not super illuminating, is a location in the broadest possible sense. Well, what does he mean by that? He means a whole bunch of different things, but what's going to be relevant for us is points in space, points in time, frames of reference. Now, a representation is absolute if it's from no point of view. So the things which are going to concern us is divorced from a frame of reference or from a particular point in space or a particular point in time. And equivalently, a representation is absolute if and only if it can be integrated by simple addition with any other representation, which I think kind of makes sense. If you've got representation from this point of view or that point of view, you should be able to conjoin it with a representation from no point of view and not come into like obvious problems. Okay, so Moore then gives an argument, what he calls the basic argument, to the effect that absolute representations are always possible. This is the thing which I've decided to skip because it gets kind of delicate and tricky, but we can come back to it if people want. So this is my and Casper's attempt to kind of streamline Moore's argument. But suffice it to say for our purposes that Moore's conclusion is that absolute representations from no particular point of view, are possible. Now what we need to think about is whether this conclusion sits well with the things that we encounter in modern physics. So my next section is about geometric versus non-geometric objects. So I'll present these to you, and then we'll see how non-geometric objects seem to be in tension with the possibility of absolute representations. So here's a bit of background. So the formal concept of a geometric object goes back to Nijenhuis in the 1950s and Schouten, but was later developed by Trautmann. And the idea is pretty simple to state. So for a differentiable manifold M, consider arbitrary point P and two arbitrary local coordinate systems around P. In order to specify a geometric object, you write down a set of components in each coordinate system and a well-defined transformation rule relating the components in the one coordinate system to the components in the other. So think about just like a vector, like you can write down its components in one coordinate system, it could be 1, 0. You can write down the components in another coordinate system, it could be 1 over root 2, 1, 1. And I have a rule relating these, which is just the usual way that vectors transform under coordinate transformations. So vectors are legit geometric objects. If the second thing is lacking, then Nijenhuis dubs the resulting entity a mere object, but we'll call them non-geometric objects. What does it mean to have a well-defined transformation rule versus not a well-defined transformation rule? Well, it's something like the transformation rule has to satisfy a transitivity property. So if one transforms the components of a given object in a coordinate system A to a coordinate system C, that should yield the same results as transforming from A to B and then to C, i.e. via this intermediate coordinate system C. If I get different stuff when I go via these two different routes, then I don't have well-defined transformation properties. By the way, I'm not going to go into it, but all of this stuff can also be couched in the language of natural bundles for those who care. So Nijenhuis did that work in the 1970s. So geometric objects and non-geometric objects abound in physics. So some examples of geometric objects include tensors, which have our usual tensorial transformation rules, tensor densities, where you have the tensorial transformation rules, but you pick up factors of the square root of the metric as well, or yeah, factors of the square, some factor of the Jacobian, sorry, at the front of the transformation. But also Christoffel symbols. So you'll all remember from your first course on GR that Christoffel symbols don't transform like tensors. You have two terms when you do a coordinate transformation on the Christoffel symbols. But importantly, these transformation rules are still well defined in the sense that I talked about before. So Christoffel symbols still qualify as geometric objects, even though they're not tensors. But we also have examples of non-geometric objects. Pseudotensors are an obvious one, but perhaps even more important are spinors. So you know that if you rotate once and you'll pick up a minus sign with spinors. So that's already showing you that spinors are not geometric objects, because going around this way and then that way versus just staying the same doesn't lead you to the same place, because you'll differ by a minus sign. You also have Yang-Mills connections on the base space. They are also non-geometric objects, and we could cook up other ones as well if we wanted to. So I'm going to focus on pseudotensors, but I do think that a lot of this material is going to be just as interesting, or maybe even more interesting and important in the case of spinors as well. I'll come back to that later. So let me say a little bit more about pseudotensors as we encounter them in general relativity in particular. So the first place that these will come up inevitably is when one's thinking about energy conservation in general relativity. And usually you'll see local general relativistic energy conservation laws of the following form. So roughly speaking, the partial derivative of the material stress energy tensor plus this gravitational stress energy pseudotensor is equal to 0. And you can derive these things in a bunch of ways, for example, by applying Noether's theorems to general relativity. But it didn't take long. In fact, almost immediately after people wrote these things down in 1918, for a whole bunch of objections to arise to conservation laws like this. So just to focus on what I think are three of the most salient, we have the following. So first, in fact, if I apply Noether's theorems to general relativity, I'll get infinitely many of these guys. So it seems like I have infinitely many distinct conserved energies, gravitational stress energy pseudotensors in general relativity, which might make me think, well, how can I have infinitely many distinct energies? That's just like weird and problematic. So kind of undermines our confidence in there being like a meaningful notion of gravitational stress energy in the theory. The second is that these conservation laws are closely related to mathematical identities, which raises questions about what their physical content is. Can mathematical identities have physical content? There's a nice paper by Catherine Brading about this for those who are interested. And the third issue is the one that I'm going to focus on, which is that these pseudotensors are not geometric objects. They don't have well-defined transformation rules. I will come back, though, to the first of these issues, this non-uniqueness issue right at the end. So it's worth delving a little bit deeper into why non-geometric objects are regarded as being problematic. It's often simply asserted that we should just use geometric objects when doing physics. Well, let's try and rationally reconstruct why we don't like non-geometric objects. So I think that one way to do this would be to think about Klein's Erlangen program for geometry, which he articulated at the end of the 1800s. So according to this, you can identify geometrical structures by specifying a set of transformation rules and considering the invariance of those transformations. So for example, if I give you the Poincare transformations, the invariant structure associated with that is just the Minkowski metric. So the objects so identified as the invariants of this class of transformations will be the objects which you could specify in a coordinate independent way, a la Malamud or Wald, if you wanted to. So you can associate geometric objects with objects specified in a coordinate independent manner by looking at the invariance of these transformations. As Pitts writes, the components of a geometric object form a natural kind mathematically. They constitute faces of one and the same entity by virtue of being interrelated by a coordinate transformation rule. What I think is interesting is that actually this isn't super novel to Pitts. Actually, Quine has the same idea at the end of his 1969 paper on natural kinds. So this idea has been floating around for quite a long time. So the fact that geometric objects have well-defined transformation rules makes them candidates for being associated with natural kinds, but not so for non-geometric objects. The reason is, of course, that non-geometric objects don't have well-defined transformation rules, so you can't really identify an invariant of these transformations. There seems to be something more ethereal or intangible about non-geometric objects. And indeed, that's the case for pseudotensors. So here's what Pitts writes about pseudotensors. A pseudotensor shares with the Einstein tensor, say, the physically interesting property of having a single recipe for inferring its components in a coordinate system from the metric components and their partial derivatives in that coordinate system. However, there is no transformation rule that allows one to infer the components with respect to one coordinate system from the components in another, so there's no mathematical unity. So I don't seem to be able to get a handle on the coordinate-free object, which is associated with a non-geometric object in a way that I can with a geometric object. And I think that's the real reason why people don't like non-geometric objects. The only way that you might seem to be able to make sense of them is as some kind of perspectival realist, where you can understand the pseudotensor from this perspective or from that perspective, but you can't get a handle on the invariant reality associated with these guys. And that's the sense in which pseudotensors seem to be in tension with this idea of absolute representations a la Moore. They don't seem to admit of absolute coordinate-free representations. So either, and again, that's the standard line, you say, well, pseudotensors don't represent anything, they're junk. And that's kind of what Eric was saying in the talk by Sebastian a couple of weeks ago. Or you try harder to associate these guys with something which would qualify as an absolute representation. And that's what I'm going to try and do now. In other words, I'm going to try and square gravitational stress energy with the Moore-Williams argument. Okay, so I need to say a bit more about the maths of pseudotensors now. So the next thing I'm going to talk about is forms on the frame bundle. So remember that the frame bundle of a manifold is the bundle whose fibers at each point consist of all of the frames for the tangent space at that point. So sections of the frame bundle would yield a frame field or a Vielbein. You just get like legs at every point. And Sabados then suggests the following interesting idea in a paper from the early 90s. So if the geometric objects in the principle of general covariance were not required to be geometric objects on the space-time manifold, but they were allowed to be geometric objects on the manifold of frames of the space-time, i.e. on the bundle of linear frames Lm over M. And if the previous coordinate and or gauge-dependent quantities and formulae could be formulated in terms of e.g. differential forms on Lm, then the contradiction with the principle of general covariance would be resolved. By this, the contradiction of the principle of general covariance, Sabados really just means the messed up, dodgy, problematic transformation properties of pseudotensors. Okay, so what does Sabados define on the frame bundle then? So let's let Lm be the frame bundle, and let's let this delta be a standard basis for Rm, and then let's let these thetas be the associated one forms on Lm. Then you can define this object sigma, which is basically just these guys wedged together, where this is the Levi-Civita symbol. You can also define, if I've introduced a spin connection relating the fibers of the frame bundle, the torsion and the curvature, as usual, via the Cartan equations. So, done all of that, Sabados then defines what he calls the Nestor-Witten form and the Sparling form on the frame bundle. The Nestor-Witten form written little u, and the Sparling form written little t. So the Nestor-Witten form is defined as the spin connection wedged with this sigma object, which I defined before. And if I take the exterior derivative of the Nestor-Witten form, it looks like this, where I've got one term with the curvature and one term with the torsion, and then one term with this object's little t, which is in fact the Sparling form, which is defined like this. Now, okay, so this is just a load of stuff, but why is this interesting? the significance of these objects proceeds via the following theorem, which was proved by a bunch of people around the same time, which is this. So for any Rm star, where this is the dual space star, valued horizontal m-1 form T satisfying dt is equal to 0. So that's basically a covariant conservation condition for this T. So this is a candidate for representing material stress energy. The following statements are equivalent. This spin connection is torsion free and this condition is satisfied, which I have in general relativity. And then big T plus little t, the Sparling form, is equal to du, where u is the Nestor-Witten form. And then, of course, if I take a exterior derivative, the right-hand side here will die, and I'll have d of t, big T plus little t is equal to 0. And these guys look suggestively similar to the stress energy conservation equations, which I saw before, but before it was written on the base space in terms of pseudotensors. Now it's written in terms of objects defined on the frame bundle. As Sabados puts it, in Einstein's theory, 3 looks like a conservation equation, while 2 gives us the superpotential for the conserved quantity. It's just the Nestor-Witten form. So again, people write down something like this, but in terms of the pseudotensor here and the material stress energy content here on the base space, where on the right-hand side, then I have an object which is called the superpotential. And again, I have something super suggestively similar, but now in terms of objects on the frame bundle. Upstairs on the frame bundle, and the Sparling form is like the pseudotensor but written upstairs on the frame bundle. As Sabados continues though, but since these quantities are defined in Lm instead of on M, and moreover T and U are only pseudotensorial forms, exterior equations yield equations on M only if we pull them back along a local section of Lm. So the point is that you can take these guys, the Nestor-Witten form and the Sparling form, and pull them back along different sections of the frame bundle to yield different superpotentials and pseudotensors on the base space. This is actually really nicely discussed in Sabados's article. So if you pull back the Sparling form, you can get the Einstein tensor. If you pull back the covariant form of the Sparling form, you'll get one of the other of the infinitely many pseudotensors, which is the Landau-Lifshitz pseudotensor. You can pull these guys back along in different ways to get all of the various different pseudotensors which people have talked about in the literature, where things like the Einstein pseudotensor, things like the Landau-Lifshitz pseudotensor, they're just some of the infinitely many pseudotensors which exist. So that's part of the non-uniqueness problem, which I was talking about before. So these guys upstairs basically encode all of the different local gravitational stress energy conservation equations, which you can derive on the base space in general relativity. Okay, so let's think a bit more about what these objects on the frame bundle are. So in a paper from 2016, I think Wallace draws a helpful distinction between what he calls coordinate independent objects versus coordinate free objects. So coordinate independent objects are objects which might be defined with respect to a coordinate system, but it doesn't really matter which one it is. It's not defined with respect to any particular coordinate system. Whereas a coordinate-free object is an object which is defined without reference to a coordinate system at all. So what are these objects defined on the frame bundle? Well, they have nice transformation properties. They're geometric objects on the frame bundle. So they avoid those problems with pseudotensors. They're coordinate independent. The definition doesn't depend on a particular choice of coordinates, but I think the right thing to say is they're not coordinate free because the frame bundle is basically the bundle of all possible coordinate systems. So that notwithstanding, do these guys qualify as absolute representations or not? Well, I think that they do. This Nestor-Witten form and the Sparling form are integrable by simple addition with any coordinate-based representation of gravitational stress energy. So these guys do qualify as absolute representations of gravitational stress energy. Now, you might worry that by defining stuff on the frame bundle, I've kind of changed the topic. So the question initially was, can I make sense of gravitational stress energy and general relativity, and does it admit of an absolute representation? Now I've introduced all of this extra machinery of frame bundles and so on and defined stuff up there. Haven't I just changed the topic to give you an absolute representation of this stuff? But I don't think so, because if I give you a manifold I automatically have the bundle of linear frames. I don't need to introduce more structure to be able to define that. And so I kind of have that for free anyway. Moreover, this I am relatively confident in, but if anyone questions it, then it would be good to discuss. But I think the following is correct. So the Nestor-Witten form and Sparling form, I claim, can also be defined using just the structure of standard general relativity, because the Einstein equation is equivalent, and this is well known, to the union of all of the different pseudo-tensorial conservation laws. And these guys and their associated dt, big T plus little t is equal to 0, just encode those guys anyway. So I think it's correct to say that the Nestor-Witten form and Sparling form can be defined using the structure of standard general relativity anyway. I would say that it's only if you choose a particular section of the frame bundle that you're introducing additional structure to general relativity, which would be tantamount to choosing a preferred frame. But if you don't do that, you can still define the Nestor-Witten form and Sparling form. Okay, so I think there's still a question about what these guys actually represent, but I think the right thing to say is, well, the Sparling form, this little t, just represents gravitational stress energy. It's just, well, it certainly plays the right kind of functional role. It satisfies the kind of conservation equation that we would expect. But it just turns out that gravitational stress energy doesn't live where we might have thought it does. It lives on the frame bundle, not on the manifold M. I think I'll skip this stuff. Okay, so thinking in this way, I think also has the potential to resolve the non-uniqueness problem, because we see that different pseudotensors are obtained by just pulling back the objects which we find on the frame bundle in different ways. So in a sense, our Sparling form unifies all of the different pseudotensors which we encounter. Good. So there are still some questions. So I think this is provable, but it hasn't been explicitly proven. That Sabados shows that all extant pseudotensors are derivable from the Sparling form. That was what I showed you before about how pulling back in different ways gives you like the Einstein pseudotensor or the Landau-Lifshitz pseudotensor. But he doesn't prove that this is possible for all pseudotensors. But hopefully we can do it. And the second is that he hasn't proven that the Sparling form is unique. So you might worry that the same issue of non-uniqueness is going to appear on the frame bundle. So one would really like to show that the Sparling form is unique on the frame bundle. So that should be done as well. But just to sum up, so first of all, I have discussed the Moore-Williams argument that absolute representations are always possible. Representations from no particular point of view, which in our case means representations liberated from points in space, points in time, frames of reference. We've seen the tension between that and pseudotensors, which don't seem to admit of that kind of representation because they don't have well-defined transformation rules. But we've seen how by thinking about things on the frame bundle, in particular the Sparling form, rather than pseudotensors on the base space, we obtain a plausible candidate for gravitational stress energy, which does satisfy this definition of absoluteness. So I think there are things to think about, like, is it plausible to think that gravitational stress energy lives upstairs in the way that I've described? And there's also the mathematical questions, which I just gestured to. But at least this is the best stab at finding something which qualifies as absolute, which could represent local gravitational stress energy. So I'll leave things here, but yeah, I'm really looking forward to discussing things. Thanks.
Thanks so much.
I have a question too.
Yeah, Peter.
So, well, the first part of my question is, when Klein defined geometrical objects in the 1920s, he had in mind only linear transformations of the coordinates, such that it didn't depend on the values of the coordinates per se. But then subsequently, as I understand it, people have considered more general kinds of transformations. So the first part of my question is, how general are the transformations that you consider in the definition of what a geometrical object is? And the second part of my question is there a reason not to use I mean, I understand the search for absolutes. Why wouldn't you go just to the invariance for your notion of what is independent of point of view? Why wouldn't you go back to say a generalization of the Kleinian program, the Erlangen program, rather than trying to make it geometrical objects per se?
Okay, so on the first part, yes, you can think about more or less rich class of transformations. And actually, this is important because if you look at pseudotensors, they are geometric objects if you restrict yourself to affine transformations, which is well known. But if I think about all smooth but otherwise arbitrary coordinate transformations, then they do not qualify as geometric objects. That's the case in which they fail this kind of transitivity property, which I was discussing. But one of the things which we take to be a lesson of general relativity is it shouldn't matter which of these latter, richer class of transformations you represent objects by, and you should be able to transform between any of that class at will. And so if your objects start messing up when you try and do that, that might be a reason to be suspicious of the object. Does that help with the first part of the question?
Yeah.
Cool. So the second part of your question.
At invariance.
Sorry.
Yeah.
Yeah, okay, so why not just look at the invariance? Yeah, so tell me if I'm not tracking the question, but it is possible to do this when you have geometric objects because you have basically a meaningful class of transformation rules, of transformations to look at. But in the case of non-geometric objects, you just don't have those transformations. So you can't really look at the invariance in the same way. Does that help? But I might not be following that second part of the question.
An invariant is always defined with respect to some set of transformations, right?
Mhm.
It's that which is unchanged under a transformation. That,
Mhm.
that fundamental notion of invariant.
Mhm.
So is it that you want this to refer specifically to coordinates? So gauge invariance, for instance, or something like that. I don't know, internal transformations that left, invariant charges or something like that wouldn't get you the perspectival invariance that you want, the perspectival independence that you want. Is that the idea?
So I fully agree that invariants are associated with a given set of transformations. I think one can move from the failure of this transitivity property, which I was talking about in the case of non-geometric objects, to there simply being no transformation rules relating the coordinates in one, relating the components in one coordinate system to the components in another coordinate system. And insofar as that fails, you can't identify invariants liberated from coordinate systems in the same way. And so it seems that all you're left with is, I know the components of the objects in this coordinate system, the components of the objects in that coordinate system, but I can't get at the invariant structure in the same way. I think that's the way to understand like what's supposedly problematic about non-geometric objects.
Thank you.
Cool.
Jacob? We can't hear you. We've got the you should join with your phone again, Jacob.
Can you all hear me?
You sound
Can you hear me?
Yes, there we go.
Can you hear me okay?
Yes, better, yeah.
Okay, excellent. James, that was a great talk. Thank you so much. So I have a couple of questions and they're related to Peter's questions.
Okay.
So of course, we have an explicit formula for, say, the Landau-Lifshitz energy momentum pseudotensor. We have an explicit formula for the Einstein pseudotensor. And these formulas are made up of, the metric tensor, derivatives of the metric tensor, Christoffel connection coefficients, the determinant of the metric. They're made up of objects that have transformation rules.
Yeah.
And certainly I can construct, say, the Landau-Lifshitz pseudotensor in any coordinate system I want. So if one takes a broader view on what it means to have a transformation law, don't I mean, if I can construct this object in any coordinate system, and in principle transform all the objects inside of it to go from one coordinate system to another, I'll get some very messy, complicated, maybe nonlinear, non-tensorial transformation law. But why is that inadmissible as an allowed notion of a transformation law? I guess that's my first question.
Yeah,
Does that make
it's always
sense?
it's always a little bit confusing, but I think the best place to look is this article by Patrick Durr, who went through these
Okay,
things more explicitly than other people have, at least to my knowledge up to this point. I mean, maybe there's some exceptions like Troutman's article in the 60s, but anyway, I think that Patrick's article is really good for taking explicitly things like the Landau-Lifshitz pseudotensor, taking explicitly its components in one coordinate system, noting the fact that the Landau-Lifshitz pseudotensor has certain dependence on derivatives is going to mean that when I do this A to C versus A to B to C, I don't get the same thing, and explicitly doing that. So
transitivity breaks down. That's very interesting. I hadn't realized that could happen.
it is weird though, and the thing that's I'm not sure I have a full grasp on yet is you start off with one coordinate system and then you move to other ones and stuff messes up. But you could choose whichever one you wanted to start off with. So something is yeah, I kind of feel
something about this is very confusing to me, because I mean, if you have an explicit formula, I mean, we have an explicit formula for the energy-momentum pseudotensor, for the Einstein pseudotensor. You know, I mean, the objects have well-defined transformation laws. If I transform them, I'm a little confused. I'd have to go back and.
Well, yeah, I mean, well-defined is maybe problematic, or could mean different things. So well-defined in the sense that there are mathematical transformation rules, but not well-defined in the sense that this property doesn't always hold.
Right.
I think the thing to do is,
okay,
like, of course, you've got the expression and you could plug in the components in coordinate system
right,
A or coordinate system B or C. But once you have done so and then you transform, that's when the problems begin. I think that maybe that's the best way.
I have to look at it more closely. Yes. So early on the talk, and I may have not. If you go back to one of the early slides, when you list the objects that you're regarding as geometric and the objects that you're not, this is pretty early in the talk.
Yeah.
It's one of the early slides. I think it's maybe before this slide.
I think it's here.
You know, you talk about like there's an wait. Yes, here we go. Yeah, tensors, tensor densities. So you include the Christoffel symbols as geometric objects, but not Yang-Mills connections. And I guess this is where I think maybe there's a nuance I'm missing, because of course the Christoffel symbols are a connection. They're a connection on the tangent bundle. And there's obviously, you know, a close analogy between the Christoffel symbols and say Yang-Mills connections. So I'm just wondering if you can explain why Christoffel symbols count as geometric objects. They famously, as you pointed out, don't have a tensor transformation law, whereas Yang-Mills connections are non-geometric.
Yeah, so Christoffel symbols count because they satisfy that property which I wrote on the previous slide. Now,
okay.
This, I think sometimes things are run together here a bit in discussions of gravitational stress energy, because of course Christoffel symbols can be made to vanish in a particular choice of frame, and that's also true for pseudotensors. And sometimes people say pseudotensors are problematic, but they have this feature, and maybe that is problematic because you can kind of always just like transform it away to zero. But I think the deeper problem, in my opinion, and at least where the asymmetry between these guys and these guys come in, is these guys have just fine transformation rules, and these guys have pathological ones, in the sense that one of them satisfies this and one of them violates it.
I have to look at this transitivity question. I think that's the key here.
Yeah. Yang-Mills connections are claim not geometric objects on the base space, but this is something that I had discussed in detail with Neil Dewar like a year ago, and we were pretty sure it's true, but I can dig out the stuff if you want to look at it more. But anyway, I'm just claiming it's true now.
Yeah, I'd love to see that if you remember after the talk. I'm sorry. Yeah, it'd be very, very cool to see. Thank you.
Cool.
Thanks.
Jonas?
Yeah, thanks. Can you hear me?
Yeah.
Okay, perfect. Yeah, thanks so much. That was super interesting. So I have a question concerning the Hamiltonian formulation of this, because I always find this stuff so confusing with gravitational energy, because it's quite clear when you have colliding black holes that they release enormous amount of energy, and we can detect that effect of that with detectors on Earth and so on. But then there's this Hamiltonian formulation, the ADM formalism, where you basically do a transformation of the Lagrangian of the Einstein-Hilbert action into the Hamiltonian formulation. And when you look at that Hamiltonian on shell, when the equation of motions are satisfied, it's identically zero, it vanishes identically. And the Hamiltonian is associated with the energy. So somehow it looks like in the Hamiltonian formulation, you don't have any energy of gravity at all. So when you look at your, so my question is, when you look at in one of your last slides, you defined this new objects, I forgot the name of it.
Oh yeah, like the nested wind form and stuff, this stuff.
Yeah, further down when you had this superpotential formulation. Further down, further down, further down. It was towards the end. When you had the pullback of the superpotential together with Einstein tensor. It was like the derivative of the superpotential plus the Einstein tensor. And it was this object T mu, I think, or T something.
Not this. Anyway, I think I know what you're talking about. Not this one, though.
Yeah, not that. That's not the slides you used. You just showed that after you show that you can do different pullbacks, and then you get different pseudo.
This one.
Yeah, but it was an equation. Where did it go?
Okay, it doesn't matter. I mean,
let's just see if it's there. There you go.
oh, okay, yeah. This is not to do with the. This is just like your standard defining the normal, i.e., base space pseudo tensor in terms of the Einstein.
Okay. Yeah, okay. But my question was just how would this look like if you would look at all of this in the Hamiltonian formulation? Would it kind of shed some new light on this question? If you would do like a ADM variables and formulate the superpotential in that? So it's just an open question.
The straightforward, honest answer is I don't know. I'm sure people have done this, and I'm sure it's illuminating, but I don't quite know what would happen.
Yeah. Okay.
Yeah.
Okay, cool. Thanks.
I mean, maybe the one thing which I can say is that the superpotential ends up being associated with like charges on boundaries. And people interested in corners in general relativity and all of this are interested in superpotentials for that reason. But that's not really directly answering your question. So.
But that would make sense, because usually when you define the energy of a system, you look at it in terms of a boundary integral. Yeah. So you can't really define the energy as located in a particular space, but just over a boundary. So somehow that seems to make sense.
Yeah. A lot of this, the best like just general resource for this material I know of is Sebastian de Haro's recent paper on energy and general relativity. It's like 100 pages long, but it goes through all of these details. But I don't think, I should check again, but I don't think he talks about doing things in the ADM formalism there. I think that is worth looking into.
Yeah. Okay. Yeah. Thanks a lot.
Okay, Mike.
Hi, can you hear me?
Yep.
Great. Thanks for this talk. This is a question sort of in the slides that followed the worry about parsimony once you move to the tangent frame bundle.
Yeah.
So this is a question, it's largely due to something Jim Weatherall said like years ago that just sort of lodged itself in my head. But I'm interested, in light of the sort of background argument that you've developed here, it's now much more relevant than it was when it was just an interesting offhand comment. If we took a non-trivial tangent bundle, and then we got the associated frame bundle with that non-trivial one, it seems like there'd be interesting consequences to doing that if we just accidentally grabbed a non-trivial one rather than a trivial one.
Do you mean non-trivial in the sense of like Cartan geometry is not?
As in its topology isn't just cross product.
I see. Okay. Yeah.
That seems like a pretty good intuition pump that there is a parsimony worry beyond that's not defeated by this kind of quick reasoning that, well, we're already committed to it. It's already there. Well, it is already there locally, but it seems like unless you have an argument that you're defaulting to the product topology, you do have to adjudicate some additional question. And because you have to adjudicate that additional question, there is some non-parsimonious ontological commitments that you're now engaged in. And so I was wondering, it's kind of a weird off-the-wall style of worry, but I'm wondering your thoughts.
No, I think that's legitimate. I mean, I suppose you could say that you're still already committed to this frame bundle in the way I was talking about, but presumably a whole bunch of other ones with different, more strange topologies as well. And then you have to give an argument as to why you would think the stuff defined on this guy is any more physically salient than the stuff defined on the other ones.
Right.
Yeah. I mean, it's just a question for you is how much flexibility do you think we have here?
Yeah, so I mean, that's what I'm curious. My own instinct is to just try to tackle head on that the lack of parsimony in this particular respect is not, a big pill to swallow or something. I just
yeah, okay, but it seems like that's something like it's worth registering explicitly. I hadn't thought about that, but I think it's a good point.
Yeah, more generally, I very much like to. Thank you.
Cool, thank you.
Okay, we have a question from Ramesh in the room.
Yeah, so early in the talk, you mentioned spin-ups as an example of a non-geometric object, in the sense you rotate by plus pi and minus pi, you get different answers. So does this bundle of linear frames construction solve that problem?
I think I wish I knew the answer to this question. In some respects, it seems to be more physically important than the pseudotensor stuff. Like, yeah, we can say that gravitational stress, well, potentially say that gravitational stress energy is not meaningful in general relativity, but throwing out fermions seems like a bigger pill to swallow. So I think we do need to tackle, like, what is the coordinate-free representation of spinors question. I'm not sure how to do it with spinors right now. I mean, it's quite possible that people have done this. I have looked into some of the maths of spin bundles and spinor bundles and pin bundles a bit, but I need to look at it more. But what you'd want to do is define some object, some geometric object on some bundle. I'm not necessarily even sure it'd be the bundle of linear frames. I just don't know. And then argue that both the bundle and the object can be obtained for free in the way that I was describing. But yeah, I right now I simply don't know whether the frame bundle is the right way to do it, or whether some other bundle is the best way to proceed. But I fully agree it's an important and pertinent question. I think it also opens more general questions about, you could ask, having considered both pseudotensors and spinors, I think this would be, well, for any non-geometric object, can I always obtain it by pulling back some geometric object on some bundle? And what is the status of those things? Those are the kind of questions which I would like to look into as a way of generalizing this project, and a way of kind of affording physical sense to non-geometric objects.
Great, thank you.
Yeah, cool.
Sebastian?
Yeah, hi James, thanks for the talk. It was great. I was, anyway, I couldn't put the camera before for obvious reasons, but I have a question kind of about at the very beginning, kind of when you were motivating
Mhm.
the talk. I was thinking like, yes, there is this kind of tendency in physics and philosophy of physics to kind of express or get worried if you get kind of coordinate dependent laws or equations or whatever, right? And I think this is relevant to what you said about Wallace, the distinction between coordinate independence and what is the other terminology he used? Coordinate
Free was the other one.
Coordinate free. But okay, but yes, so there is this kind of tendency to go, I guess, into more geometric structure. So even for example, when presenting simple Newtonian mechanics, depending on what school of thought you are, you might want to go into manifolds from the beginning and like do the thing with simultaneity, whatever, right? Kind of Friedman, Ehrman, and then later a lot of people from Irvine and Oxford and so on. But you also have the other school, I guess Harvey, as you know, I guess that where you try to like think of physics in more practical kind of terms, and like you endorse from the very beginning this idea of deriving more abstract laws from how things behave in the lab and like the rods and the clocks and all of that, the dynamic approach, right?
Yeah.
And not only Harvey, but also in other literatures, like in symmetries, where you go into subsystem, kind of you try to understand things from the subsystem perspective instead of like the whole universe perspective and the more absolutist, so to speak, perspective. So having said all of that, I just wanted to push a little bit, or at least see your opinion about someone who would say, well, you know what, I'm happy with physics being very dependent on your point of view, so to speak, like in some ways, like I'm happy that everything is tied to the frame or to the lab. And then obviously I want to be able to find ways of relating different frames, but I'm just happy with staying in this bare bones kind of approach to physics, and not so worried whether or not there is this geometric object that maybe would allow me to transform in this cool or nice way between these different frames. Well, I guess what would you say to someone like kind of saying something along those lines?
I mean, I'm, as you know, not averse to Harvey style ways of thinking and associating, say, the physical significance of Lorentz transformations with how subsystems behave under boosts and all of that kind of thing. But I think that, I mean, what Harvey would say about the Minkowski metric is that its physical significance is inherited from the behavior of such physical systems under such kind of transformations. Yes. But I think that, and that's all fine for me, but I think that actually even Harvey, I mean, I don't want to put words in his mouth, but this is what I guess he's going to say is maybe he would say that gravitational stress energy doesn't seem to have any significance in general relativity, because there is like, you don't have any like well-defined thing which is going on. I could take my subsystem and boost it in one way or boost it this way and then another way, and I get different stuff going on. Right. So I think in that way of thinking, you would not be inclined to regard there being anything like, if you know what I mean, anything interesting associated with something which isn't transforming in that nice transitive way in that case. So I guess I mean I think it's great to connect up with these different ways of thinking about the status of geometrical quantities and stuff liberated from coordinate systems in physics. I think that Harvey is still going to say that geometric objects and things liberated from coordinate systems do have physical significance in virtue of how physical things behave. But I think that for the same reasons, he's not going to think on the face of it that gravitational stress energy has any physical significance. So it may be orthogonal, but it's still worth thinking about.
Yeah, no, good. Thanks. I suspect that. Yeah, that's good. That's a good answer. Thanks. Yeah.
Jonas, did you have another question, or is that just stuff from before?
It just stuck.
Okay, Jacob.
I had one very quick question. I'm trying to think about the concern about spinors. So it is true that if you rotate a spinor 360 degrees, you get a minus sign, and that's weird. But spinors do have a well-defined transformation behavior. And of course, there are other quantities and objects in some of our theories or our conjectural theories that have weird behavior under transformations. And here I'm thinking of things like pseudo-vectors, pseudo-scalars, like if magnetic monopole charge is a thing, then it's a pseudo-scalar. Why should I say that it's okay to have a pseudo-scalar, and that could potentially be something I could, regard as a geometric thing, but that spinors with their weird 720-degree rotation property, I can't.
So you're talking about spinors just then reminded me that the thing that I think all of us interested in these things should study more is Brian Pitts' excellent paper on spinors, where he goes into how spinors are almost geometric objects and the sense in which that can be okay. Right. So I think that's the thing for us to look at. In terms of the magnetic monopole point, the cases seem analogous to me, but maybe I'm wrong. So insofar as you'd be worried about the one, you should be worried about the other one. But if you think that's the wrong thing to say, then
we're out looking for magnetic monopoles.
Yeah, but
people are looking for them, and I don't know how would we regard magnetic monopole charge? It has this weird behavior under parity transformations, which scalars shouldn't have.
Mm-hmm.
But it is a well-defined transformation law. It's certainly transitive. I guess I'm a little confused about, like, would there be a dispute about magnetic monopole charge the way there is about spinors? I'd never heard anyone suggest that could be a problem. Or take magnetic fields. Of course, a magnetic field vector, right? Of course, now we know that in relativity, magnetic field vectors are embedded into, an antisymmetric tensor. But, is there a problem with the fact that you have vectors that don't change direction under parity transformations? Is that a reason to discount them as being geometric? It's.
Isn't the right thing to say about electric and magnetic fields?
I just don't know.
Then they are not geometric objects, but that's not necessarily worrying because we've learned to unify them in something which is a geometric object.
Right.
Whereas spinors, we don't know how to unify them yet.
Yeah. All right.
Okay. Well, we're
I'm so curious about yeah. Okay. Thanks.
Yeah, we're running out of time here, and the colloquium needs to get started. So let's all thanks James again. Thank James again for a wonderful talk.
Yeah, thanks everyone for coming. Great questions as well.
See you next week, everyone.
Thanks, James.
Thanks. Bye. See you all soon.
Bye. Very nice.
I didn't get it.